Maybe we'll start introducing. So welcome everybody. This is our first solar climate intervention virtual symposium for this year. And we'll welcome you all. We are excited to have two very good speakers. I will introduce the first speaker. This is Arju, Dr. Arju, who has been at NCA, a postdoc for a year. And now he is working as a chief climate scientist at Aurassure. And he's going to talk about his recent paper, which is called South Asian Summer Monsoon Under Stratospheric Aerosol Intervention. Okay, so we'll have about 20 minutes of the presentation. I give you a warning about 5 minutes before the end, and then we'll have questions afterwards. Okay, go ahead.
Okay, so thank you everyone for giving me an opportunity to discuss my paper here, and thank you Simon for introducing me. Good morning and good evening to all of you based on your time zone. And today we'll just discuss on this paper recently published in NPJ Nature Group. And maybe it's some people are calling this as an anomaly, or some people are calling it is the reality, but it is now in news that Earth reaches 1.5 degree climate limit for the first time in 2024. And this is from ECMWF, and this image shows that most of the days in 2024 actually cross the 1.5 degree limit when it is compared with some pre-industrial average. The same time, if you'll see, the internet is flooded with both positive and negative news on geoengineering. So, I mean, people are questioning our ethics, people are questioning about the mechanism, and some people see some hope in that. So, I mean, let's see that, let's realize that now people are taking this as a, very much seriously, whether it's positive or negative, time will speak. And climate change and stratospheric aerosol intervention, I think all of you are experts, so I don't need to go much detail why it is there and how it is there. But I'll take you to this slide where I'll talk a little bit on the rationale behind this study. So as we know that Psi successfully reduced some risks. So modeling studies say us that Psi can successfully reduce some risk associated with increasing temperature, like heat waves or loss of sea ice. But the South Asian summer monsoon, which is a very kind of important process in the climate system, is least studied and least understood under SAI scenario. There are few studies. Professor Bala and his group and few other researchers have done some studies, but all them mostly are, kind of idealized experiment. I think Professor Bala also presented a very beautiful talk a month back, I guess. So those are mostly approximated by reducing the solar constant or using the single point SO2 injection. Again, the driving mechanism under which the SAM precipitation may change are unclear and least explored. So this work, so we decided to do some analysis to understand like how the SAM precipitation changing under Psi and what are the governing mechanism or the possible mechanism leading those changes. So we designed, we just use the, and okay, so before going that to the mechanism and results, so I'll just give little introduction to those people. Those are not actually experiencing monsoon or studied monsoon during, their research because of their diversified region and research interest. So South Asian summer monsoon is one of the strongest component of the global monsoon system, contributing to more than 80% of Asia's rainfall. And the socio-economic condition of India and Asia is largely depend on the ISM rain. And in recent time, there is a significant decreasing trend in the summer monsoon rainfall. And those are confirmed through various observational data sets and modeling studies. So the left side one is the classical monsoon picture. Basically, we all studied during our introductory classes of meteorology or maybe in geographies. So there is a land ocean temperature gradient theory where the land is warmer during the summer and ocean is cooler. So there is a difference in the pressure and eventually a circulation takes place, and that brings more rain to the land mass and we get monsoon. But the recent year, there is a new paradigm that it is just not the dynamics and thermodynamics of land sea temperature constraint, but there are many different processes they play a larger role in addition to the land sea temperature contrast and moist static energy. Those are notably the greenhouse warming, land use changes, and aerosols, alongside the dynamics and thermodynamics and teleconnection patterns. So this is the current trend, and these are from one of the very important paper recently published from Roxy Group. So they are claiming that India as a whole, the mean precipitation is actually in a declining phase. That is similar to the point number 3. But the extreme events have increased threefold since 1950. So there are more extreme rainfall, but at the same time, the mean precipitation trend is actually declining in central Indian region, or maybe in the Indian monsoon region, you can say. So to study more, we have used the GLANCE data. Basically, as the community, they are very much aware of these data sets. So these are the model. Basically, the model is the community air system model version 1. And the injection strategy is actually sulfur injection have been done at the lowest stratosphere, 5 kilometers above tropopause and at 4 different latitude. And the target is to actually maintain the temperature gradient, interhemispheric temperature gradient, and equator to pole temperature gradient, and to keep it at the present level using a control algorithm. Just a second. And the simulations, as we know that GLANCE, we have 20 ensemble available to investigate, but so we have just used 3 ensemble just to be as we know that in the size scenario, in the future RCP scenario, there are only 3 ensemble available. So to make the analysis consistent, we have just taken the first 3 ensemble and investigated in this paper. And these are some results. As you can see that we have just focused over the Indian monsoon region, and we have investigated mostly how the mean precipitation is changing, how the extremes are changing, and what are the driving factor behind that. So here we can see in the first image, the left-hand side is the how the precipitation is changing under the warming scenario compared to the control. So all are actually so whatever we'll see throughout the presentation are basically the anomaly results are basically the anomaly difference between either RCP against the control or the SAI against the control. So the left-hand side is showing that there is a kind of reasonable increase in precipitation across the monsoon domain, and that is most of the CMIP 5 and CMIP 6 model studies are also agreeing that under a global warming scenario, there is an increase in precipitation over this region. But in the right-hand side, if we'll see that there is a strong decrease in the precipitation under psi scenario, this is psi minus control, over the central Indian region. But interestingly, the precipitation is actually not decreasing everywhere, but it has increasing and decreasing pattern, there is a decreasing pattern over the central India, but increasing pattern in the southern tip, and again increasing pattern over China and other over Arabian Sea as well. So this positive anomaly actually, this positive and negative anomaly actually created an interest to investigate why this precipitation pattern is actually forming. So what could be the possible reason behind that? Below figure, this is again the average map, and you see that in the RCP there is an increase in rainfall, but in control and SI there is a reduction in rainfall, and these are the percentage change. So clearly you can see that there is a strong reduction of precipitation over under the SAI scenario, and those are close to like 22 to 25%, which is confirming that Under SAI, the Indian monsoon precipitation is experiencing a drought-like condition. Then further to investigate this precipitation, spatial precipitation pattern, we looked into different atmospheric processes. So this figure is more or less explaining the major mechanism which is actually controlling the precipitation. So what we observe, so this is the first, the figure 2A is showing the temperature anomaly. So you can see that under this sulfate injection strategy, there is a strong increase in the temperature that is close to 8 Kelvin over the lower tropical stratosphere. And this is exactly in the location of the two jets. And due to this increase in the temperature, we observed a weakening in the subtropical jet stream. And maximum reduction of the strength is observed at the core of the jets. And at the same time, we investigated the meridional wind anomaly. This is a very well proven mechanism, and especially in the forced aerosol simulations, we see this, sometimes we see this kind of pattern that whenever there is a weakening in jet, and even immediately we can see a wavy kind of condition in the atmosphere. So they are kind of linked to each other. So we observed a change in the 200 hectopascal meridional wind anomaly during the June, July, August, and they are resemble to a similar structure of Rossby waves, and they are linked to the like positive and negative kind of pressure anomaly, or you can say that cyclonic or anticyclonic pressure anomaly. If we'll go to the D figure D, that is actually presenting the structure of 200 hectopascal ASEAN summer monsoon anticyclone, which is also a very important parameter which is persistent over the monsoon time. And if you closely see that it is splitting the monsoon anticyclone into two, and it is creating, it is more toward, it is making anomalously cyclonic. So these two important parameters are actually contributing the updraft and downdraft over the land at the same time, the wind pattern in the surface. So as a combination of, as a response of these two changes, we can see a strong subsidence over the Indian landmass, and there is an anomalous weakening of the southwesterly wind over the Indian landmass, which is the driving force for Indian summer monsoon during the June, July, August months. So these are actually contradicting, and these are actually slowing down the monsoon strength. And if we look into the figure C, the meridional wind anomaly is very closely matching with the observed precipitation pattern in the figure 1. So the red is actually contributing to the drying, and blue is contributing to the wet phase of mean summer monsoon rainfall. In addition to these changes, we also found a change in the atmospheric state variable and cloud cover. These are actually going hand in hand with the precipitation pattern. So we saw an anomalous increase in the geopotential height and sea level pressure over the vast area of India, Pakistan, and Middle East. So remember that during monsoon, there are usually low pressure over the land and high pressure over the sea. But if you will see the figure 3C, the surface pattern, pressure pattern is actually flipping, and it is making higher pressure over land and low pressure over sea. So it is changing the traditional pressure pattern, which supposed to be differently in the monsoon period. And this is because there is a strong subsidence. And that is also reflected in the geopotential height and the like the upper atmospheric, like 850 hectopascal temperature. In addition, there are a notable reduction in the cloud, total cloud cover found over large part of Indian landmass. And this is also observed in the total cloud, but in contrary, the low cloud anomalies possess a special pattern. There is a clear north-south anomaly kind of dipole pattern, and similar that is close to similar to the precipitation anomaly we saw in the figure 1. Another feedback we observed during the analysis, that is called dust feedback. Observation studies indicate that dust induced warming is highest ever Arabian Sea, and there are many studies that reported that this extreme warming or the higher radiative forcing over the Arabian Sea during the monsoon time actually strengthen the southwesterly monsoon flow. But under SAI scenario, under SAI, we found that there is a strong reduction in the dust over the Arabian Sea, and this might further exacerbating the monsoon reduction. And these are already reported in previous study that under SAI and RCP there will be a reduction in the dust. But we observed another interesting feature over the Indian landmass, where we found that there is an increasing dust burden over the Indo-Gangetic plain. This could be due to the anomalous reduction of the rainfall over the land. And this positive dust anomaly also many significant impact on the regional climate as well as regional radiative forcing. So there is a contrasting pattern of the dust coming out under the SAI scenario, and we may need to do more investigation to see what could be the other impact from this dust changes.
You have 5 more minutes.
So again, the last few slides, so we also observed the extreme precipitation under SAI. As you know that there is a declining trend in the mean precipitation, but there is an increase in precipitation, extreme precipitation. And India witnessed many floods and many lives lost during this flood event. We found that there is a notable reduction in the extreme precipitation. Basically, we plotted the percentiles, and you can see in the 95 and 99 percentile under SAI, there is significant reduction in the precipitation, and those are actually giving some insight that SAI may reduce the precipitation extreme, but there may also reduce water availability due to the concurrent reduction in the mean rainfall. So these are the take-home messages. Basically, as we know, or this is what we discussed. So it is reducing both mean and extreme precipitation, and that is because the use of sulfate aerosol results heating of the lower tropical stratosphere and inducing wave-like wave-like structure, weakening the northern hemispheric jet stream. We also observed a strong relationship between the wave structure changes and the geopotential height anomaly and the strength of Asian summer monsoon anticyclone, and the weakening of the strength of Asian monsoon anticyclone further changing the pole pressure anomaly as well as the wind pattern in the surface. And in addition, the heating of the lower tropical stratosphere is actually increasing the tropospheric static stability, which further reduce the tropical convection. And the feedback like dust is also playing a role in modulating the Asian summer monsoon rainfall and the regional climate. So these are some caveats in the study. So as we know that this is a single model investigation, so additional model analysis is needed to identify inter-model differences. And as we know that rainfall extremes can have more immediate economic and social effects, so we need to have special focus to investigate the rainfall extremes under SAI. And further model experiments are needed to understand the mechanisms better. This is a kind of first attempt, and we need to dig more details to understand the mechanism and other processes. And these results do not advocate for stratospheric aerosol engineering deployment, but we aim to enhance our understanding of its regional climate effects like SAM. And recently, I think Professor Robert's group published a nice study how it is impacting the agriculture that has just came. I was just looking the paper today. And before considering SAI alongside the emission reduction, um, we need to study its impact on human earth system or the natural system. Just a single slide, I'll discuss 1 minute. So this SRM research, as we know, that it has a large bias under when we compare the global north and global south. For an example, the recent study suggests that there is only less than 50 paper published from India, even though we are contributing to, I think, 1/5 of the population of the total global population. So we need a fair governance because the climate vulnerable community in the global south must lead and participate in research and decision-making processes. So these are some solutions for that. Maybe we need to help them access the knowledge in much better way, and we have to involve the academician, researcher, and support groups. We have to consult community to evolve a shared vision on the strategy. And we have to provide learning content and opportunity for education and discuss the research among different groups, as well as, we can actually create a network between global north and global south to minimize this gap. And with this, thank you so much for the opportunity, and I'm happy to take some questions.
Thank you very much. Very nice talk. And we go now to our discussion. We already have a question in the chat, but hi, Alan, you already have your hand up, so maybe you're the first. Go ahead.
Okay, thanks. That's a very nice paper. It agrees with Simone's classical paper on looking at monsoon response from multiple models in the first round of GeoMIP. But I was wondering, precipitation is so variable, but you only use 3 of the available ensembles. I think it would be really interesting to look at the rest of the ensemble members. Now that you know how have the software to do it, it would be pretty easy to see how much difference it makes and see how significant the results are. And also just a detail about plotting. I think it's much better to stipple the parts that are not significant rather than the parts that are significant, because when you stipple the parts that are significant, you cover up what you want people to look at.
Well, actually, we have done the analysis for all the ensemble as well, but I think there is only 3 ensemble available for one of the simulations and to make it the result consistent, that we are not taking 20 against 3. So we just thought of taking the
why is that a problem? You can average the control runs and compare to the average of the 20 ensembles, and you can look at the natural variability because especially when you're looking at precip. I don't think a particular control run doesn't correspond to a particular ensemble member. It doesn't matter if they have the same initial conditions. So I think you're sort of throwing away some information. Of course, you're looking at a RCP 8.5, which is a huge signal. So the signal won't be as strong in other simulations, but you've got it. So why not look at it?
Yeah, sure. We'll just we'll just extend the analysis maybe based on your suggestions and recommendation. Surely we'll just have a look into the simulations.
Okay, for some reason, oh, there you are. You put your hand up. Okay, and I think the next, again, I guess you also asked about September. I think September, we did analyze that too, but right, I mean, you can quickly answer that too if you want.
I thought the
Okay.
the classical monsoon season extends into September. I was just wondering why you left it out.
Well, so we have given a region in the paper itself. So because most of it's again a different way of different groups, like the classical people, they take September, but most of the aerosol people, they took June, July, August. And some people studied the relation between June, July, August and June, July, August, September. And there is a 95% correlation between the rainfall. And if you'll ask me today, we are not getting the rain in June. So even June is not an ideal way to include in the in the monsoon calculation. Again, few researcher like the very good researcher, maybe Professor Alan and other people, know that the B.N. Goswami and other group, they are claiming that the northeast should not be included, northeast part of India should not be included in the monsoon calculation because they start getting rain from the May. So they want a different monsoon from May to maybe September rather than June to September or June, July, August. So there are so many different way people look into monsoon. But we have given one of the reviewers asked the same thing to us, why you didn't include September. So we have given a rationale why we choose June, July, August instead of June, July, August, September. So maybe you can have a look into the paper, but I'll just happy to give you, hundreds of reference those have used June, July, August, and maybe thousands of reference who have used June, July, August, September. I'm still learning.
If the answer is it doesn't make any difference, that's a good answer.
Yeah, yeah.
Okay, great. Let's go to the next person. Moritz Günther, you were next, please.
Yeah, hi, thanks. Maybe I'll get my video to work as well. Yes. Yeah, thanks. This was very interesting. You had this one slide on the mechanisms, and I think I understood what was going on in the lower troposphere, but I didn't quite understand what you said about the upper tropospheric mechanism. Like there was this Rossby wave coming in, and I wondered if you could expand a bit more, like where does it come from and why is there this pattern? Yeah.
Well, I mean, because this is an average, so maybe it is not very ideal to say that it is just, the Rossby wave is creating from somewhere and propagating. But there are few study, they reports that similar kind of structure where when there is a weakening in the jet, this is creating a wave-like structure that is similar to a standing Rossby wave. But again, this is a mean pattern, and we can just say that and not in a very detailed way that whether it is propagating from one place to other, or whether that pattern may change in maybe next 15 days, or including another 1 month of simulation in the analysis.
Okay.
So basically, the heating creates somewhat is related to the weakening of the subtropical jets, then creating that standing Rossby wave. Is that correct, Aju?
Yes, a kind of that is the mechanism proposed.
And that standing Rossby wave is correlated to the rainfall changes.
Rainfall changes. Basically, it is creating the anomalous cyclonic and anticyclonic pattern and regulating the subsidence and updraft in the surface.
So basically, the heating has a strong correlation to the
because the monsoon is a kind of, there are multiple factors associated together. So which is first and which is last, distinguishing that is pretty difficult from a mean kind of, average, monthly average data sets, what I understood. And another thing is that at the same time, there is the weakening of the upper atmospheric, the ASEAN summer monsoon anticyclone, we also observed that. So whether that is deriving the updraft and downdraft, or the jet stream is driving the Rossby wave and that is changing the updraft and downdraft, is really difficult to distinguish.
Okay, thanks.
Yeah, thanks. And there was, I think, a question by Ping Ping. Did you have a hand up or?
Yeah, I have a hand up if there's still enough time. I was wondering about the dust feedback. That sounds really interesting. And I was wondering if dust is directly calculated in the model, or is there a way that you get the dust information, especially for the future climate scenarios?
Simon, can you just answer that question? How dust is calculated?
I mean, you interactively calculate the dust in the model. So the dust emissions are actually connected to the wind changes and also the land relative humidity, how dry it is. The drier, that's where you see the increase in the wind, in the dust when it potentially gets drier to the reduced precipitation. But you also see changes in the dust coming from the Arabic area, right? Because you get changes, you get reduced rainfall there, so you get less dust. I think that was the mechanism. And so that is all connected and simulated in the model.
I see. Thank you.
Okay. Any other questions to Aju's work? If not, I hand it over to Matthew for the second talk. Thank you very much again.
Bye-bye.
Thank you, guys. That was a great talk. So our next speaker is Dr. Ping Narenpitak from the National Electronics and Computer Technology Center in Thailand. And Ping will be talking to us about the regional impacts of SRM on precipitation in mainland Southeast Asia. So Ping, the floor is yours.
Thank you. So let me share my screen. Okay. Can you see my slides?
Yes, it looks good.
Okay, sounds good. So yeah, we're shifting from South Asia to Southeast Asia, but we're still in the theme of precipitation. Before I continue further, I would like to acknowledge my colleagues who are co-authors of the paper, Cyril, Saifon, and Siriwat. They are like within the same team, and they also work at National Electronics and Computer Technology Center. This work was funded by the Degrees Initiative, and also I would like to thank Ben Kravitz and Pete Irvine, our collaborators who helped gave feedback to this work. Okay, so this talk will be based on a recent paper that we just published on regional impacts of SRM on temperature and precipitation in mainland Southeast Asia. So the picture that you see on the left is our domain of the study, which is 5 countries in mainland Southeast Asia and then the adjacent oceans. Here in the paper, we use GeoMIT-6 simulations, 3 experiments from them, G6 sulfur, G6 solar, and G1 extended. But for the interest of time for today, I will focus on the outputs from G6 solar and G6 sulfur and the SSP2 and SSP5 simulations. So for this study domain in mainland Southeast Asia, we cover 90 degrees east to 110 degrees east, and then from the equator to 30 degrees north. In this domain, there are actually 2 climate systems that we're looking at. The subtropics, which is from 10 north to like the top of the study domain. And there are 3 main seasons, like winter from November through February. And this is really mild winter, unlike the mid-latitude winter. Summer from March until May. And then the rainy season begins in July through August, or sometimes September too. And that is like the influence from southwest monsoon. I think it's quite connected to the monsoon in like over the Indian Ocean, right? And then the rainy season here in Southeast Asia, mainland Southeast Asia, continues until October. During the eastern part of the study domain that you are looking at here, this area is affected by the tropical disturbances like easterly wind, etc. And then the area south of 10 degrees north, this is a tropical climate where there are mainly 2 seasons, summer from March until September and rainy season from October until February. So like I wanted to mention this first because as we look into precipitation later on and we look at different seasons, there'll be 2 like kind of distinct climate systems that we will be looking at or are we talking about. So just quickly going through the models that we use 6 models from GeoMIT-6 simulations, and I think you're all familiar with this, so I'm going to go through it quickly. Like we use SSP5 8.5, SSP2 4.5, G6 solar, and G6 sulfur. Now, as a reminder, G6 solar is a reduction in the solar constant, whereas G6 sulfur is injecting sulfur aerosol into the stratosphere, and mainly in the deep tropics. And then in this study, we averaged the output to like 2 periods, the mid-century and the end of the century. The end of the century is 2070 until 2099. And like it's a 30-year average just to cover all like the decadal variability in the output as well. So before we go to precipitation, I wanted to talk about the temperature quickly. On the left is a time series of historical temperature from all the 6 models. And then on the right, these are the temperature average over the study domain for the 4 experiments that we looked at. And I mean, it's pretty clear that the high emission scenario increases the temperature a lot by like almost 4 degrees Celsius. But SRM and SAI in the tropics in both G6 experiments can keep the temperature at the temperature of SSP2 simulations. We did look into how the temperature in each month changes. So the black line on the lower left panel is the historical average from, I think, the last 30 years of the historical simulations as well. The yellow color is the average from SSP2 4.5, and that's the end of the century. So we see warming in this region, but warmer during August until February. So after the rainy season, toward the winter, we see more warming even with medium emissions. Now we compare the other three simulations with SSP2 4.5 simulation, and that's on the lower right. With higher emissions, there's even more warming, and that's to be expected. With SRM and SAI, both G6 solar and G6 sulfur show slightly warmer June, July, August compared to SSP2, and then slightly cooler during the winter. So spatially, I would like to focus on the top row and the bottom row. The top row is the difference between SSP5 and SSP2. So the warming is everywhere, but warmer in the subtropics. And I think this is as expected too, that we will have more warming in higher latitudes. Now with G6 solar, so the difference is not statistically significant. That's why we had the hatches over those areas. And the patterns are pretty similar throughout 4 different seasons, from December, January, February on the left, and through SON, like September, October, November on the right. What's interesting is with G6 sulfur minus SSP2 4.5. So in the winter and the summer, like DJF and MAM here, there is more cooling in G6 sulfur compared to SSP2 almost everywhere over mainland Southeast Asia, except over Myanmar, and also in over the oceans. Whereas in the rainy season, there is mostly warming in over mainland Southeast Asia, but still slightly cooling over the oceans. So these cooling and warming patterns will play a role later when we see the precipitation, as differences in temperature does affect changes in the wind, and so the convergence of the moisture. Okay. So now we're moving on to precipitation. Here, this is annual precipitation, the sum of all over the entire year, historical on the left and future climates on the right. So SSP2 and SSP5 have increased precipitation. G6 solar has lower precipitation than the first 2 simulations. What's interesting is with G6 sulfur that we see increase in precipitation faster or more so compared to the SSP2 and SSP5 simulations. But after the middle of the century, after 2050, G6 sulfur has much lower precipitation than the 2 SSP simulations. In terms of the season, we already see changes in precipitation in the seasonal cycle, even in SSP2 4.5, that there is less precipitation during the period that is supposed to be rainy, but more precipitation in the period that is supposed to be drier. Changes in monthly precipitation is interesting too, and here again, in the lower right, we compare these changes with SSP2 4.5. So SSP5 8.5 has more precipitation than SSP2 during the June, July, August period, the monsoon period. G6 sulfur has lower precipitation than SSP2 4.5 almost throughout the year, except for the late rainy season, October, November particularly. Spatially, again, now here I'm comparing SSP2 4.5 and SSP5 8.5. So there is delayed monsoon even in the climate change scenarios in the future. So in June, July, August, the southwesterly wind becomes weaker, and that just reduces the moisture convergence. But still there is increased precipitation in mainland area. In September, October, November, the southwest monsoon does get stronger. So it's like what Asu said in his presentation, here in Southeast Asia, we also see a shift or a delay in the monsoon from the Indian, like that brings the moisture from the Indian Ocean to mainland Southeast Asia. And we see this even in SSP 5 8.5 simulations. In DJF and MAM, there is less precipitation almost everywhere, especially over the oceans. And if you recall these, well, yeah, sorry. So, and yeah, if you recall, like the area south of 10 degrees north, in December through like April or May, this is the rainy season in that region. So this also shows that in like with warmer climate, these regions will have less rain during the time that they're supposed to get rain already. With G6 solar and G6 sulfur compared to SSP2 simulations. In G6 solar, again, the changes are small, but overall a reduction in precipitation, except for in DJF when there is more moisture convergence in Western Myanmar, that there is like slightly increased precipitation. Again, what's interesting is with G6 sulfur, during the monsoon season, like June, July, August, you see that in the southern part of the Stadino mainland over the oceans, the southwesterly wind becomes weaker, but and then there is reduced precipitation. In September, October, November, the southwesterly monsoon wind becomes stronger here, but the increase in precipitation is not as strong as what we see in SSP 5 8.5. But the change in the wind patterns of the monsoon is still very similar. In DJF through MAM, there is pretty much reduced precipitation in the southern part of the study domain, in G6 sulfur as well. And over these regions are also where we have more cooling at the surface compared to SSP2 4.5. You might wonder how robust are the models when it comes to precipitation output. So we average like different ensemble members of each model, and they are plotted here. So for SSP2 4.5, the precipitation, the amount, and the wind direction, they're pretty consistent among like all 6 models. But for SSP 5 8.5, in terms of the change in precipitation, there is pretty large intermodal variability. Some models suggest increased precipitation over mainland, whereas like 3 of them suggest no change or a slightly reduction in precipitation over mainland Southeast Asia. So it's like not as robust now. With G6 solar, I mean, the change are small and pretty much a small reduction in precipitation. What's interesting here again is G6 sulfur minus SSP2 4.5. All 6 models agree that over the oceans and in the area south of 10 degrees north, there is reduction in precipitation everywhere. And when you look at the multi-model mean change in precipitation, like on the lower left panel, there's no hatching over areas south of 10 degrees north. So this difference, this reduction in precipitation is statistically significant. Now, 4 models in terms of over mainland Southeast, the over mainland area, 4 models show slightly reduced rainfall, while another one, MPI, both the higher and lower resolutions, show slightly increased rainfall over mainland. And again, these plots that you are looking at are the averages during the end of the century, 2070 until the end of the like 2099. But if I were to show you the plots from the middle of the century, which I mean, I did not include them, but the differences or the reduction in precipitation is a lot smaller. Like in the middle of the century, changes in precipitation is not as strong as what we see toward the end of the century. We also looked at the distribution of precipitation. So on the left is 99th percentile of precipitation, or the extreme. And on the right is the dry month occurrence, which is the number of grids or months with precipitation less than 1 millimeters per day. So first, with higher emissions, SSP5 8.5, toward the end of the century, there's a lot more extreme precipitation. However, dry month occurrence also increased in SSP5 8.5. This shows that with higher emissions, there's both more extreme precipitation and more drought in between the very rainy period. Whereas for G6 sulfur, SAI in the tropics does reduce overall precipitation, and it also, of course, leads to more drought occurrence. I wanted to show you quickly that aside from precipitation, we recently submitted a paper that looks at sea level rise, but here we focus on Thailand, or like one station, like a little bit over Vietnam, but mostly over Thailand. Here we compared outputs from 3 GCMs with the observations being tide gauges and the altimetry. We saw that GCMs are able to represent the seasonal cycles of the sea level well, but when it comes to the trends of the sea level rise, it does get trickier because at least this is a unique problem to Thailand, that there has been pretty strong land subsidence in the late 90s in Bangkok. As you can see on the right, the blue line shows relative sea level rise. The blue line is for a station in Bangkok. And you can see from 1970 until like 2005 or 2010, the rate of increase in relative sea level rise is really steep. That is from land subsidence, from groundwater extraction. So like one of the challenges that we face as we look at sea level rise is to like convert the observed time series, which are relative sea level, to absolute sea level, which is the output of GCMs. But most of the stations we have like GCMs show consistent sea level rise trend. So we are then able to take GCM outputs and compare sea level in different future climate scenarios. The first column on the left is just an average along the coast of the Andaman Sea, which is the western part of Thailand. The second column is the average along the coast of the Gulf of Thailand. And the right column is the global average, which is a direct output from GCM. So we see that SSP5 8.5 obviously has much higher sea level than the other 3 simulations. What's interesting is G6 sulfur has slightly lower sea level than G6 solar and lower than SSP2 4.5. The difference in G6 sulfur and G6 solar here is partly from less ice sheet melting in G6 sulfur, and that has to do with the wind circulation, that the wind and the current, the ocean current, that melts less of the western, the ice sheet in western Antarctic. So with here, like, so if you recall in this, with precipitation, I showed that in SSP5 8.5, there is more extreme precipitation toward the end of the century, but there is also more, like more occurrence, higher occurrence of dry episodes or like droughts in between the rainy periods. Here with even in like higher sea level, this can cause some further issue, not just with water management, but water quality of the river that exits into the ocean, which there are actually like 3 in Thailand, and I believe there are more along the coasts in Southeast Asia or in many regions. So with like more drought and increased sea level, the salt water can push back into the river, and this just contaminates the quality of the river, of the water. That's another problem that could happen. But if sea level rise does not increase as much, say in like, for example, G6 sulfur simulation, then well, salt water intrusion might still become a problem, but at least less severe compared to SSP5 8.5. So to summarize, here I have like a table that shows what happens in SSP5 8.5 compared to G6 sulfur in the mid-century and the end of the century. The reason I showed differences for mid-century and end of the century for SAI is because the impacts are different. In the middle of the century, when the amount of cooling that is needed is smaller than the end of the century by the design of the models. And so amount of injection is lower and the changes in precipitation, other things are also smaller. So here with the rainfall, again, with higher emissions, there's more rainfall, especially extreme precipitation, leading to more floods. With like SAI in the middle of the century, there's pretty much no change in rainfall when we compare to SSP2 4.5, but toward the end of the century, there is reduced precipitation, and that also leads to challenges in water management, as a lot of the countries in this region relies on rainfall for agriculture. Well, so here I alluded to the drought problem, that it will for sure be an issue if there is less rainfall, but with higher emissions, there are also more frequent drought periods. And then for sea level, this pretty much goes with changes in the surface temperature. So here I wanted to point out that I think even though it's not a direct comparison, we can still see that when there's like intense SAI toward the end of the century, we see a lot more extreme changes versus moderate SAI in the middle of the century doesn't see as big of a change. Also here, the different impacts of climate change versus solar geoengineering means different infrastructure investments and adaptation strategies. So this also indicate that as different countries, different regions plan for that adaptation strategies, like it's going to be challenging not knowing for sure how the future would look like. But I mean, of course, that's one of the challenges in anything anyways. And also like mainland Southeast Asia is still a pretty diverse like region, with some of the cities being highly developed, whereas some of the cities still need development, even if they are in the same countries. So the impacts that different individuals feel about climate change and solar geoengineering will also be different depending on where they are and a lot of other factors. Well, to summarize, we show that SRM can help lower temperature and slow down sea level rise in mainland Southeast Asia, but it does reduce precipitation, which can pose some risks on water management. We see that there is delayed monsoon rainfall during June, July, August, and September, that the rainfall starts later, sometimes not in June, but like closer to July and lasts longer. This change in the wind patterns and the seasonal cycle leads to increased overall rainfall in the SSP5 8.5 simulations. I mean, there is more rainfall, in SSP5 simulations, but in SRM, even though we see similar changes with the wind patterns, there is reduced overall rainfall. SRM with little to no mitigation leads to extreme changes in precipitation, but what we see with GeoMid 6 in the 6 models is that moderate SRM during the middle of the century leads to that leads to less cooling, may not lead to as much of a change in precipitation. Now here, because there's also the factor of time, like comparing middle of the century versus the end of the century, it is still not a direct comparison, like between just the difference in amount of injection. We also see that there is reduced precipitation observed in the deep tropics, like near the latitudes of the injection in G6 sulfur, where there is more surface cooling and more warming in the stratosphere. And this change in the temperature profile in the deep tropics leads to more stable atmosphere that weakens the overturning circulation in the tropics. So here it's one of the examples that showing that site of injection probably matters, and also that like stratospheric warming would lead to reduced precipitation. There, again, different communities would feel different impacts of climate change and SRM, depending on where they are, but also like just other factors. And for the next step, we will be looking at regional impacts of marine cloud brightening. And that is all I have, and I'll be happy to take any questions.
Thank you, Ping Ping. That was really interesting. Andrew, do you have a question?
Yeah, there are two effects that you described on the rainfall that I noted. So there was one where you said that a monsoon might arrive a little later, and the other one where you said that in at least one of the ecoregions, you'd have a situation where your wet season became drier and your dry season became wetter. So there was like a muting of the seasonal effect. Now, neither of those sound like they're necessarily directly damaging, but can you at least estimate? I appreciate your model didn't give this as an output, but could you at least estimate what that might do to the ecology and agricultural output? Is this something that we need to worry about, or is this just a minor change to the pattern of precipitation that's not going to have any kind of real world damage to people?
That's a very good question. I don't know much about the ecology part, whether that much change in precipitation would affect the ecology, but I can pitch in on the agriculture part. I think what matters here will be about water management, because at least in Thailand, from what I observed, farmers rely on like previous knowledge a lot. So when there are changes in precipitation like this, it becomes a challenge for them as they plan on their like growing season, for example. Yeah, but it's something that I would have to think further to like give a more thorough answer.
Thanks. Are there any questions? Other questions from people? If not, I had a question on G6 solar versus G6 sulfur. It looks like in your plots there were quite big differences between the two. And I was just wondering if like you looked into why those differences were there for the regional climate in Southeast Asia.
Yeah, so for precipitation, one of the reasons that we think contribute to this difference between G6 solar and G6 sulfur is because G6 solar pretty much reduces over like average solar constant. So there is no stratospheric warming component in G6 solar, whereas in G6 sulfur, there is injection of stratospheric aerosol that leads to warming in the stratosphere. And the stratospheric warming is something that affects the tropical precipitation.
Yeah, okay.
Yeah.
That's what I thought. But,
yeah.
Cool.
Thank you.
If there are no other questions, then I think we can stop here. Thank you very much for your talk, and thank you, Asutosh, for your talk as well. If anyone else would like to share their research in the near future, please let me or Simone know. And with that, thank you again, both. It was great. And I'll put the video online at some point, so I'll let you know when that happens. Yeah, thank you very much.
Yeah, thank you, everyone.
Thank
Bye.
you. Bye.
Thanks a lot.